thank you for giving this lecture. And you are gonna talk to us about a biased introduction to six-vertex model. Thank you.
Okay, yeah, thanks a lot, Francesca, for the nice invitation. And yeah, it's also my great pleasure to be back to GGI, even just virtually. So, and today I will talk about some, some like basic introduction to six-vertex model, which is supposed to be pedagogical and simple. So please interrupt me whenever you have any questions or you think some place is not clear. Yeah, and before I really start with the lecture, just want to briefly motivate you why this is interesting to look at six-vertex model. So to begin with, yeah, so the reason why six-vertex model is interesting, there are many different reasons. If you're interested in statistical mechanics, well, it is a very nice model to study thermodynamic properties and phase transitions of such a toy model. And if you're interested in condensed matter physics, well, the Hamiltonian limit of the six-vertex model is the famous XXZ spin chain, where you by using integrability you can solve many interesting physics of the quantum spin chain, which is the center topic of condensed matter physics. Or if you're interested in high energy physics, it's also very useful because there's the renowned ADS-CFT integrability and also beta gauge correspondence, where this six-vertex model serves as the simplest example where some energy theory models are closely related to. Or if you're a mathematician, it's also very interesting because especially recently, there are recently developed integrable probability theory where six-vertex model is also very basic building blocks in this theory. So with that all being said, hopefully you're motivated. So we start with to define basically six-vertex model. So it comes from a very old study on ice. So maybe in the 1930s, Pauling has studied the entropy of ice in 3D. And basically for water molecule in the crystal limit, so when they form ice, basically for one oxygen atom, there are 4 neighboring hydrogen atoms, 2 of which they form like a chemical bond. With the other 2, they form some sort of hydrogen bond, which is weaker. So we can put this into a diagram where if they are connected by the chemical bond, we put an arrow that goes into the vertex, which centered by this oxygen atom. And the dashed line, which correspond to the hydrogen bond, we put arrow going out. Okay, so for example, this configuration in the ice crystal, it corresponds to this diagram. And even though Pauling studied the 3D version, we can think of even simpler case, which is ice in a 2D square lattices. So we essentially put this constraint or this so-called ice rules into a 2D square lattices, and then we can study basically the statistical mechanical properties of that model. And normally, if we have if we put arrows to the edges of these square lattices, we would probably expect 2 to the power of 4, which are 16 configurations, just because it can either goes in or out. But because of the ice rule that I was describing, namely 2 arrows goes in and 2 arrows goes out, it reduces to only 6 configurations, which is which I denote here. And all these 6 configurations, in order to study the statistical mechanics of it, I need to put Boltzmann weight to each configurations. So in this case, well, I use this A1 for the Boltzmann weight of this configuration. And if I invert all the vertices, I call it the weight A2. And then there's B1, B2, C1, C2. So there are 6 possibilities. Yeah, and then we can, in principle, arrange, let's say, these 6 possibilities into a matrix form. So, so in the sense that I would call this matrix, which is actually it's rather a tensor, with the 4 indices, so alpha, beta, and gamma and delta here, in this way. And if I have an arrow goes in, to the right, so basically alpha takes the value 0, and then beta takes the value 0 again if it's also to the right, and so on and so forth. And similar also for these 2 indices. Then I can arrange this R into a matrix here. And moreover, you can think of this as this R matrix acting on the endomorphism of 2 tensors C2. And this implies that maybe it's nice to think about this R matrix as a, as 2 spin 1 halves, acting on 2 spin 1 halves. One basically living in this space, I call it 1, so alpha and beta here. And then there's another spin 1 half live here, so on gamma and delta here. And moreover, if this Boltzmann weight satisfies some certain condition, so in this case, okay, first of all, I would like to consider a very symmetric configuration. So I assume that A1 equals A2 equals A, and the same for B, and for C. And moreover, if A can be parametrized by some function in this way, so by some hyperbolic sine function, and Boltzmann weight for B, I set it to be 1. So this is of course arbitrary choice, because in order to calculate the partition functions, we can always rescale it, and it will not affect any physics of it. And for C, we have here, so hyperbolic with eta here. And you see that now this depends on two complex number. First is U, and the other is eta here. And essentially, what I will show is that the model is it only depends on, I mean, the physics only depends on the value of eta instead of, both U and eta. And so this is my parameterization. So I'd like to choose this parameterization, and we can see how this R matrix will satisfy. And here, I would like to also to consider, essentially, I can put 2 spectral parameters for each of the vertices. So each of the edges. So for the horizontal one, I choose U as a spectral parameter, and for the vertical one, I choose V. And in this specific case, this R is a function of just the difference of U and V. So this is, of course, a very special R matrix in this case. So in general, it depends on both U and V, so 2 complex number. And this is sort of defined as R12 of U. So what's really remarkable is that if you choose this parameterization, you can show that this R matrix satisfies this Yang-Baxter equation. So here, maybe I need to specify that, okay, I'll just add another page. So R12, it acts on essentially, so C2, C cross C2. So sorry, I need to multiply by identity at 3. So it acts trivially on the last C2, but it acts non-trivially on these two Hilbert space. And similarly, if you have, you know, a 2, 3, it's essentially the same. So I hope this is clear, that it acts trivially on this Hilbert space, but non-trivially here. So that's why there's this 1, 2, 1, 3, 2, 3, etc. And then it's an exercise that if you use this parameterization, you can show that it satisfies this condition. And what's the physical meaning of these Yang-Baxter equations? Well, if you're a field theorist, you might think of it as some scattering matrices of particles. And the Yang-Baxter equation implies that any three-body scattering in 2D, so it can always be factorized into two-body scattering, and it yields the same result. So there's no particle creation, and moreover, the scattering between like 1, 2, 1, 3, 2, 3 is the same as 2, 3, 1, 3, 1, 2. Yeah, so this is essentially the physical meaning of the R matrix. And here, as a statistical mechanical models, those existence of these Yang-Baxter equations will guarantee us to construct commuting row-to-row transfer matrices, as I will show to you.
Sorry, Yuan, if you allow me, can I ask you a question?
Sure, yeah.
May you elaborate more on how you can see the correspondence from these R matrices with the scattering process in 2D?
Yeah, so, okay, here I'm a bit abusing the notation here, but in principle, you can also think of, instead of these R's, you can think of this S. Well, and in the meantime, all these U and V here, you can think of it as basically the rapidities or the momentum of the particles. And if you think like that, then essentially this becomes the factorization of like, let's say this symbolize essentially the scattering between 1 to 3 to 3 to 1 process. And these are essentially the product of all these S matrices. And if they equals to each other, it means that it doesn't matter what the order of the scattering processes. And it also means that the three-body scattering can always be factorized into two-body scattering.
Okay.
But of course, for S matrices, it has to satisfy more conditions. For example, there are some you know, some requirement on basically where the poles are and some you know, analyticity conditions, etc. But here for the R matrices, it's much more relaxed. So at this level, they just share the same form. In principle, you can take, let's say, a field theory limit of this model, and then you will get maybe you will get like a Sine-Gordon theory where you can really define all these S matrices. But at this stage, it's not really there. So, and I'm not going to use this actually. I just want to motivate you that, yeah, physically they are very similar.
Thank you.
Yeah, you're welcome. Yeah, so then I would like to consider an object that's called a monodromy matrix. And monodromy matrix here, if you write it explicitly, well, this M A of U psi n, where n runs from 1 to L. So there are, let's say, okay, sorry, n to capital N, because I use here. So this operator is essentially a product of AN. So where the A is simplify the physical space that's called auxiliary. So you will see in a moment. Here is, since I showed you, it's U minus psi n, and then we have AN minus 1, U minus psi n minus 1, dot 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 to RA1, U minus psi 1. Okay, so I just consider this operator. And the reason why I would like to consider this operator is that it satisfies this Yang-Baxter, this RMM relation. I will explain here. So what this diagram means is that if I have a R matrix here, which is called RAB, so this is A and this is B. So RAB at U minus V acting on this A of U psi n, and here I have MB U psi n here, sorry, V. By applying the Yang-Baxter relation, which I showed here in this diagram, recursively. So I first apply with these three, these three indices with the Yang-Baxter relation, and then I will essentially move this R matrix to the right. In the meantime, I exchange A and B in this matrix, and as you can see, you can do it recursively. So you can push it all the way to the right, which is called train argument. We will arrive at some relation such like that. So we have MB, and then here's MA, and then the same R matrix. And the importance of that is that if I consider another object called transfer matrix, which is a partial trace over this monodromy matrix, over this auxiliary space, this object transfer matrices, they commute with each other, simply because, if we, if we multiply also by the, let's say, the inverse of this R matrix, suppose that it exists, what we have is this relation. And then we take a trace over A and B over these two left-hand side and right-hand side. What we get is essentially T, U, okay, it also depends on the so-called inhomogeneity psi. And then here we have TV, the same, equals TV, TU. So what it means here is that now we have two operators, and they share, like they have different, they depend on different spectral parameter, and they commute with each other. Actually, they commute with themselves with different spectral parameter. And this implies that if we do a power expansion over this T, in principle, we can, so in principle, if we write T of U as a power expansion, so sum over, let's see, n from 0 to L. Okay, and now I'm being a bit sloppy here because in order to deal with it, we need to think about the exponential of U, where it will become a polynomial. But in some sense, up to some normalization, this should be the case that it's proportional to U to the power of, some in to the power of UN, where in is some operator acting on the Hilbert space of this 1, 2, 3, 4, etc. But somehow this in is not the best way to look at this model. Instead, maybe it's better to consider the logarithm of this operator. So somehow we need to assume maybe this operator is invertible, but it's really irrelevant. So we consider such a expansion. And since we know that all the log of TU also commute with log of TV, so and it's true for any order of this UN, this implies that all these Qn and Qm are commute with each other for any n and m are essentially positive integers. And this is this gives us some relation to essentially the existence of infinite conserved quantities for some quantum Hamiltonian. So if we think of if we consider a model where all the psi n equals 0, so this is called homogeneous limit, and we do a log derivative, we define such operator, so Qn. So these Qn's are essentially the expansion over the spectral parameter u when u is small. And when we consider Q2 with the 6-vertex model that I showed you before, so namely using this parametrization, what we will get is a quantum Hamiltonian, so-called XXZ Hamiltonian. And to write it explicitly, we have we can write it in terms of spin 1/2 operator in this way. Where this delta here equals the hyperbolic cosine of this eta parameter that I showed you before in the 6-vertex model. Yeah, and then this implies that since I was telling you that Qn commute with any Qm, it means that this quantum Hamiltonian Q2 commute with infinitely many quantum operator Qm. And another thing which is not obvious at all, but somehow is true, is that all these Qm, they are local operators. So they are operators with local density. Sorry, I have to say it. So in some sense, Qm is an operator can be written as sum over h, let's say m plus 1 to, okay, sorry, not m, let's say h n plus 1 to n plus m, roughly speaking. So they are operators with local densities, which is, of course, will have a very proper field theory limit, etc. So this is really the defined properties of quantum integrable models. So essentially, this Hamiltonian is a quantum integrable Hamiltonian. But I will not talk about that, not mainly talking about that today. So in the meantime, if we think about this monodromy matrix, we can arrange it in such a way that all these, in these 2x2 matrices, where they are the element in this auxiliary space. So in this space, so here, in this A here. And the matrix element 0, 0, which is here, is essentially considering this matrix element. So we fix somehow the boundary of this line. And then we get essentially this operator A, which is the 0, 0 element of this in this auxiliary space. And then the partial trace over this A is essentially A plus D. And moreover, this B can be pictorially described in this way. So here is like 0, 1, and C is essentially the opposite, is this one. And one interesting fact is that B operator, it acting on all downspin state equals 0. Yes. Yeah. So this B operator is more like a creation operator in some sense. Yeah. You can think of it as some kind of creation operator. And moreover, from this equation, so here, sorry, from this equation, it tells us about some algebraic structures between these ABCDs. So these are called beta algebra, and the spectral generating algebra of this object is so-called Yang-Yang. It's a quantum group, but it's not really important here. So what's really important is that for the eigenstates or eigenvectors of this transform matrix can be written in terms of some set of quantum numbers called beta roots, and they can be written in this way, that it's kind of a B operator acting on some vacuum. And and then the number of this B operator stands for the number of quasi-particles, it says excitations. And in this spin chain language, they are magnons. So they are essentially spin, they are just like turning a spin up to a spin down, this kind of excitations. And in order to satisfy this relation, so T acting on some state is eigenstate of this T, and using the algebras of the B and C, what we will obtain is that this UG satisfy a set of coupled nonlinear equations. So they are more or less in this way. So from 1 to n, and then we have hyperbolic psi minus psi m. Sorry, it's not it's uj plus eta over 2. So eta is some parameter, if you remember. Uj minus psi m minus eta over 2 equals to product of k not equals j m, where m is essentially here is the number of these B operators. And then we have sine uj minus uk plus eta sine uj minus uk minus eta. And the physical meaning of the right-hand side is essentially these are the kind of the scattering phase between two quasi-particles. And then on the left-hand side is more like some quantization condition, because it's a quantum system. We need to put it with in this case is periodic boundary condition, and this simplifies the quantization condition of the scattering phase. And this is the famous beta equation. So where has beta used to solve essentially the Heisenberg XXX model in the 1930s, and it's still beta equations are very important even nowadays, even in the context of, let's say, gauge theory or whatever. And then we move on to a specific, because I mean we are solving essentially a statistical mechanical model. So what's really important here is essentially the partition function. And obviously, partition function depends on your boundary condition. For example, the one simple example is to, let's say, consider a periodic boundary condition in this horizontal direction. Let's see here. The periodic means that you identify these vertices with this one. So it's like put it on a cylinder. Or we can also consider in both direction periodic boundary condition, and then we essentially on the torus, etc. But in this talk, I want to focus on a very specific boundary condition called domain wall boundary condition. A domain wall boundary condition in this context means that for this horizontal line at the boundary, all the arrows are going in. So you see that, let's see, on this boundary is all arrows going in, and also on the right boundary. And on the, in order to keep the number of vertices conserved, I want to consider all the boundaries here on the up and down boundaries to be arrows going out. And this is essentially the definition of a domain wall boundary condition here. And then I want to consider a partition function of such domain wall boundary condition. And this object is interesting because people can use it to prove some, some useful formulas. For example, the like the overlap or the norm of these so-called beta states. But today I'd rather focus more on the mathematical point of this boundary condition, which is the configurations of this domain wall boundary condition is in one-to-one correspondence to the number of so-called alternating sign matrices. And alternating sign matrices are some combinatorics object. So it's also called ESM. And it's a matrix that consists of 3 elements. So either is +1 or 0 or -1. And moreover, there's a requirement such that the sum over each row and column has to be +1. And moreover, so for any non-zero element after a +1 has to be a -1. And also the non-zero element that after -1 has to be a +1, etc. And moreover, sum over each row and or column of this AN equals +1. And this means that, for example, we take these configurations. So you see that here for this row, well, there's only one non-zero element, which is +1. So sum over this row is +1. Also here, and moreover also here. So because +1, -1, +1. So the sum over this row is also +1. And then we immediately see that for each row or column, the first non-zero element has to be a +1. And maybe there is a -1, and maybe not. Maybe there's only just one +1 here, for example, here. So these are the rules. And moreover, there's a very interesting question on how many there are those alternating sign matrices. And so it's a very important kind of combinatorial objects, and people have studied it because, for example, to look, there are some connections to so-called lambda determinant, etc. But what's really interesting, there's a nice observation by Cooperberg, which is very nice, is that the configurations of this domain wall boundary condition for 6-vertex model is one-to-one correspondence to the configurations of ASM. And the rules are actually very simple. So for any of this C1, so this is a C1 vertex, you replace the C1 vertex by plus here. And for C2 vertex, you replace by minus sign here. And for the other A and B vertices, you just put 0. And because of the boundary condition, it automatically satisfies all the definition of ASM, as I was explaining before. Because, for example, for the first row, we see that it has to change the direction once. And basically, C vertices change the direction. All the A and B's, for example, here, or this is a B vertex, it doesn't change the directions. So then we also know that it has to change the directions odd times. And then by essentially identifying this fact, we can find one-to-one correspondence between the configurations of the domain wall 6-vertex configurations and the ASM, the number of ASM. So in order to get the enumeration of the ASM, essentially what you do is you can put all the weight of this A, B, C vertices to be 1. If in that case, well, the partition function is simply just count how many configurations there are. And there has been like conjectures on this AN, which the exact form is not very important. I will show you in the end of the talk. And what Kuperberg did in '96 was just to, instead of try to find a way to calculate this AN, he used some known result in physics on what are the partition functions of this 6-vertex model. And then by putting all the Boltzmann weight to 1, we automatically get the ASM. He proved the ASM conjecture. And in order to continue, I also need to get a little bit technical. I need to, put some, to explain how to calculate this partition function. So I need to define some variables such as xj, which is a so-called exponential of uj. So for each of these horizontal line, we put a spectral parameter u1 here. This is u2, etc. And then on the vertical one, I put like psi1, psi2, etc. And then I want to use the exponentiated version of this spectral parameter. And in the ABCD language that I showed you before, this is nothing but overlap between two states. So for example, here is so here is like a spin up here, and then here spin down, and then acting on this B operator to this spin up. Or equivalently, if you think about in the left, from the left to the right, essentially rotate these partition functions by 90 degrees. What we get is product of this C operator here. And this is, okay, in condensed matter physics, maybe this is more like calculating some overlap of some states. But let's do it another way. So first of all, we know that this B operator, they commute among themselves. So this is a fact from the algebra of this ABCD operator. So all this all these B and C operators commute with themselves, and this implies that if we take this partition function as a function of these variables xg and yj, it's a symmetric function in x1 to xn, and also symmetric function in y. This is very important later on, because I want to show to you that this partition function is more or less a determinant. And we know that determinant, you can shuffle each row and column without changing the value. And in terms of these variables x and y, these A and C vertices are written in this way. Okay, the exact form is not very important, but B is always 1. And then what we do is to consider the structure of this symmetric function of all these variables. For example, we want to consider a pole at xn to yn. So as we can see that there will be poles if in this in this row and column to have either A or C vertex. And you can try by yourself, but you can more or less convince yourself that there are only poles if we choose a C vertex at this point. So because at this corner it can either be a C or B vertex. If it's a B vertex, there's no pole. There's the only pole that coming from the C vertex here. But if we put a C vertex here because of the ICE rule of the 6-vertex model, all these okay, 1, 2, 3, 4, 5, 6, 7, 8, all these 8 vertices are fixed, and they are all has to be like a vertex, but there's no pole because I'm only considering the pole when xn goes to yn. And what's really interesting is that since all these ones are frozen, so we essentially have a smaller partition function. And very interesting fact is that this smaller one, it also satisfies this domain wall boundary condition. So what we have is that if we expand over this xn goes to yn limit, what we will have is a first order pole here, and then plus something regular, and this pole proportional to essentially a smaller domain wall boundary domain wall partition function. And this is more or less very similar. If you're familiar with determinants, you can expand it to be sum over minors, and this is essentially what it is. So okay, then we can conjecture that the partition function is such a determinant, and the reason why this is true, you can try to, for example, try to check the property that there's a pole here. It's also symmetric in x and y. Yeah, and then there. So this is essentially the correct solution. So you can try to convince yourself that this partition function of the domain wall boundary condition is a determinant multiplied by some nice functions here. And then, but in the end, what we really want is not arbitrary x and y, but what we want is all the essentially all the Boltzmann weight of these configurations to be 1. And if you look at here, so how could we do that? Well, we need to send u minus psi to be I pi over 3. In the meantime, eta equals I pi over 3. So for example, if we look at a vertex, is a sinh u minus psi plus eta over sinh u minus psi, and we want this equals 1 and also c equals 1. So first we realize is that, okay, so u minus psi should be eta plus minus 2i pi over 3, and moreover you also want to satisfy this. So in the end you are left with the only option, which is eta equals I pi over 3. And in the meantime, all these u and xi's are homogeneous, and the difference between them is I pi over 3. However, okay, so first of all, you can rewrite this this partition function in this our familiar variables u and xi. What you realize is that if you, for example, if you put all the u's together, they diverge here. For example, they diverge here, or the x's together, they also diverge. But in the meantime, you will have some zeros appearing here. And also there will be divergences here. So so it seems a bit you know, pathological limit if you take this limit. And indeed, we need to do something smarter. So we can, for example, define UG as VG plus I pi over 3. And then what we do is we just need to send all the V1 to Vn and Xi1 to Xin to 0 of this partition function. And this is essentially equals to this equals to the partition function with A equals B equals C equals 1. And as I explained, this is the enumeration of alternating sign matrices. So we just need to focus on this kind of diverging part here. Because for these two parts, these two just constant that are that will appear here. What's really non-trivial is to take the limit when all the v's and xi's goes to 0 of this operator, sorry, of this determinant. And here maybe I need to use a bit of a trick, some trigonometric identity, which is you know, which I want to replace this part by using this identity. And what we can get is essentially nothing but, okay, then I also need to rescale my VG and Xi in a very smart way. So so this is kind of arbitrary, because I mean there are many ways of calculating this limit, but I just decided to use a rather cute one, well, so using some trigonometric identities. And then what we get is this AN can be written in this way. So yeah, so we just have this limit when the psi epsilon goes to 0 of this object. Yeah, and then there's a bit, again, some trick that yeah, it's related to some Cauchy determinant identities, Cauchy-like determinant identities. Yeah, one can try to prove that this determinant of this ratio of these two hyperbolic functions can be written in this way. And then by taking the limit when psi, sorry, epsilon goes to 0, we can just cancel all the divergence of this zeros and infinities of this product. And what we have in the end is a, so for example, here it gives you to the 3 to the power of something, and here this product give you this product. And yeah, and then this is more or less the end of the proof. So by evaluating these partition functions to this specific value, what we can show is that the number of ASM equals to this number. And this number, by some rearrangement, it can be written as this ratio of 2 factorial. And this is exactly what's written down by Mills, Robbins, and Ramsey in the 80s, where they conjecture that the number of alternating sign matrices to be this number. It has been proven by Zauberger maybe in the 94 or 90, yeah, early 90s, using some complicated mathematical objects, using some partitions of integers in this combinatorial way. But then it was really remarkable is that Kuperberg, by using, so for example, the partition function, this partition function is known before Kuperberg by Korepin and Izergin. And Kuperberg used this nice determinantal formula, and by taking this specific limit, he managed to prove the DSM conjecture again using very, very simple argument. So that's essentially the beauty of six-vertex model, which we start with something very, very general, and in the end we can prove some difficult mathematical conjecture just by taking some special limit of this partition functions of six-vertex model. And of course, it goes beyond that. So, for example, even though we proved the enumeration of this ASM, there is also some other mathematical question, which, for example, about, for example, the fluctuations of the uppermost class, or like what's the when the system size of the matrices goes to infinity, and so on. And this is more like a modern studies of so-called integrable probability. Where people study all these objects. But for today, as just an introductory lecture, I will stop here. So, so hopefully you will find six-vertex model to be a very beautiful and nice model. In the meantime, it can be used to prove some mathematical conjectures, which seemingly unrelated somehow. Thank you very much for your attention.
Thank you. Thank you very much for your very nice talk. And I guess we will have now time for questions. I have a couple of questions, but let's wait for shy audience.
Hello, can I ask something?
Hi.
Yeah, sure, please. Yeah, hi.
Thank you for the very nice lecture. I was wondering, in your calculation, you started from the XXZ model, and then you wanted this A equal to B equal to C equal to 1.
Right.
And then you say that in order to obtain it, this eta parameter should be equal to, I don't remember, like pi over 3.
Yes.
I was wondering,
can
you... can you repeat the same calculation, but instead starting from a simpler version of the XXZ? Like if you start from the Heisenberg model?
So the... so essentially, XXZ model is the homogeneous limit of the six-vertex model. I need to take all the inhomogeneities to be 0 or the same. But here, in order to calculate the partition function in the determinant form, it's easier to consider an inhomogeneous version of it. So
in that case, sorry.
So in the end, I'm not doing any calculation with the spin chain in some sense. It's purely just calculation with the vertex model. And I'm interested in finding this partition function. And this partition function is easier because if you consider the homogeneous limit, which in the end is what we do, the problem is that there will be some poles and zeros that needs to be canceled. And it's kind of easier to do it backwards instead of directly start from this homogeneous limit. It's like a usual trick that people do. They consider they consider, let's say, a more complicated object and then take some limit and then you to get your answer. Yeah, so this is the logic here. Yeah, and so for all the Boltzmann weight equals 1, it's indeed related to XXZ spin chain, but it's not exactly that because, yeah, it's just a special point of the transfer matrix.
Because in that case, you would have to take this eta to be, well, the delta, the inhomogeneity parameter equal to 1, and then the U, the spectral parameter equal to 1 as well, right? Because the Heisenberg will be identity plus U permutation. So in order to get all the weight
so
at
the Heisenberg point is not the combinatorial point. Yeah.
Oh, okay, I see. So that is the So if you start from Heisenberg, you don't get the you cannot formulate the problem.
Yeah, you can still calculate the partition function, obviously.
Yep.
Yeah, it's also some determinant, right? But that's not that there has nothing to do with the combinatorics here. Okay, maybe it has something to do with it because typically you can define some object called n enumeration, so something called n enumeration, and this is essentially like let's say you choose A equals B equals 1 and C equals n, so you put some additional Boltzmann weight to to your C vertex, and okay, and then okay, you want delta to equals to 1, where this is A squared plus B squared minus C squared over 2AB. So this means that you need to choose C equals 0, apparently, right? Yeah. So then it's a limit where okay, in the combinatorics point of view, it's a bit a not very interesting limit. Yeah. But yeah, but people are trying to do different things, right? So so if you're interested in combinatorial objects, then maybe delta equals 1 is not a very interesting point here. Yeah.
Okay, thank you for your question. Is there any other question? So maybe I will ask one.
Okay.
So I mean, I'm not an expert, so just to grasp some concepts. You have been talking about 2 dimensions, and it looked like 2 spatial dimensions, and it looked like time was unimportant for you. So
yeah, because the statistics is a statistical mechanics. So there's no time.
Okay.
Yeah. But if you think about like more like yeah, quantum, because I was explaining that so this transfer matrix commute with the quantum Hamiltonian here. And there is a one-dimensional quantum spin chains, so they are spin 1/2 coupled to each other, but they are arranged, let's see, in a 1D geometry, and there you can consider time and the time evolution of these states, and this can be solved using these techniques, like this kind of, you know, algebraic Pedanza techniques. Yeah, and in the meantime, you can also think of this as kind of imaginary time, which is temperature, and then you can study thermodynamics of this quantum spin chain. Yeah.
Yes. So if you go to higher dimensions, everything breaks down?
Yeah, that's a very good question. So for higher dimension, everything breaks down. For example, the factorization of scattering. However, there are something which is still left, which is, so this is called Yang-Baxter equations, right? So in 3D, which is 2 + 1D if you want, there are so-called tetrahedron equations by Zamolodchikov. And there you cannot think of this as scattering of particles. Maybe you can think of it as scatters of strains, for example. And there you can also get some, you can also find some like commuting transfer matrices. Yeah, so all this, for example, all this, you can also construct something, but in a you know 2+1D in two. Yeah, basically the transfer matrix will act on a 2D lattice. Which also implies there exist some commuting quantities and so on. But the problem there is that, first of all, I don't think these objects are local there, so which limited the application to it. And moreover, the algebraic structure of such solutions are less known. So for example, here, there are many known mathematical structures using, let's say, Lie algebras or quantum groups to the representations of those mathematical objects to study this model. But in the 3D case, it's less known. Yeah.
Okay.
So, so in a nutshell, it breaks down. But there are some special exceptions where one can do something, but not very much. Yeah.
Okay, thank you. Okay, so if there is no other question, I would like to thank Yuan again, and to thank you so much. And also I would like to thank everybody, because this lecture concludes the series of 2023, if you want, theory lectures by young researchers from GGI. But I would like already to announce that there is a new batch of GGI postdocs, and so you will know soon if there will be another series, and maybe to people that participated, they can start thinking if they want to give their lecture, and just contact the new postdocs, or also us, because we will still be in touch. Thank you very much.
Yeah. Okay. Thank you, Francesca, for organizing this year. Yeah. So thank you.
Thank you. And this was a very nice way for starting the day for people in Italy or Europe. And while I would like to tell you, thank you for this late afternoon effort, and have a nice evening.
Yeah. Don't worry. Yeah. Thank you. Yeah.
Thank you.
See
Bye.
you. Hope to see you soon. Bye.
Bye. Bye.